Hi, foolish. Alright, I'll wait for another minute and I'll start recapping. Spider! Hey! Nice to see you. Alright. So, easiest way to do this is just go here and find out. So, stream 16 was the most recent one, other than this one. So, what I did from there is, so just proper pass stuff. So this isn't important. All these utility stuff. Utility, universal do transformation. I want to show that off. Yep, that's if transformation as well. Yep, these are all to do with the same thing. Yep, var forwarding. Yep, same thing. Yep, ret forwarding. They're all the same thing. Okay, and then target specific thing. So arc. I'm doing arc platform with instead of target triple, I'm only doing two things. I'll explain that. This thing's just something separate, side effect correctness, ZST removal, and some other stuff. So I'll go over it quick. It's easier if I just, what is that? Okay, so we'll do forwarding. So let me block this out. They can go all the way up to the top. So I have these things up here. Swipe. The easiest one to do is probably this one here, expa underscore forwarding. So I can show you what happens. No. Here you go. So after here, HIR reorder, we're left with the normal function in itself. So all it is let a equals if, and then that if is its own if, and then another if. So essentially, you've got these nested like that, right? All right, so let a equals this, right? And what happens, HIR typing types it, and then it inserts the BRK to break out of the do block, and doesn't do much else. But here's the important part, HIR normalisation. So if you look here, main.export forwarding, it opens the if statement, and forwards that let a variable. It forwards it into the cases here, and then returns it. Now, you may think like, in other cases, here, if without this let a, if you did something like this and just deleted that and just made it return that, it would do something different. It would create its own temporary variable. See how it's created the own temporary variable, and it looks basically completely the same, except for the fact that it's not using the a. So if you look here and show them side by side, you can see. So a is forwarded up, a is forwarded up. One is separate, one separate, one separate. Good. So that's how it works. Essentially, you're forwarding the assignment as essentially of forwarding it into places where you would need to create these temporary variables. So let's show a different example. Something like yeah, this one. Fact iter All right, so this one is with loops. Okay, let me just bring this up to the top. Bring this in here. So you can see it's just iteration, and you're essentially doing this let take 2 here. So let take, and then you're breaking. So F1 to so just F equals take, and then here you can see in the BRK here, take equals F. I mean, that's simple. You're essentially forwarding the result location, not RLS like zig semantic. It's nothing like that. It's just simply instead of doing this take here, you can essentially just do this. Just do take equals F. Be okay with that. Instead of introducing a temporary variable like _0 right here, right? So that's a change that I did. It's like a small optimization sort of thing. It's like a mini optimization. It has more benefits than an optimization though. There's a reason why I wouldn't do it. I wouldn't do it if it just did that. Hey Buford, welcome back. So, yeah, and universal do transformation. That's another thing. Hi Jamie. Yeah, so if propagation. So, this is probably one of the pretty easy things to understand. Instead of creating a temporary variable, these control flow constructs, the if, the do, the loop, instead of creating a temporary variable to store the location of the expression, because essentially we're performing normalization, a statementizing, turning this functional code into this more simpler C-like code. So I mean, yeah. So this is one of the easiest things to understand. Instead of creating a temporary variable, if it's already being assigned, just assign it. But there's also another thing. There's also another thing that you can do. So let's take a look at this. Remove that, and let's just remove the ret a, and let's just put ret in here. Just put ret in here, and we'll see what happens. So we'll run it. Actually, hold on. Let me just comment out this. All right, then we'll run it. Yeah, take a look here. So, yeah, forwarding, typing. It just inserts a BRK, but you already have the ret, so this BRK is going to go away. You're just BRKing with no return. So if you go here, HIO normalization, what it does is it forwards these returns, the rets, upwards, right? That's one of the simplest things. It works for locals and it works for return. One of the simplest things that have been implemented. So there's a couple things that I did. So I did this normalization, the forwarding of locals, and I can show you where it's done. Essentially, you're going down here and you're calling this function called nhir x per target. Just stands for normalize HIR x per target. Essentially, you're calling it with a list of statements and the expression and the target. And essentially, what the target is where you eventually want it to go to. So, and this is where the forwarding works. So, if expert.kind equals expert if it's applicable to be forwarded, forward it with nhir if target target loop target target do target target. Else, this is where I can't find a place to forward it. And then we'll go here. It'll call nhir expert and essentially normalize it. And then we'll go to here, switch target. So I have two different things. So enum is just defining enumeration with r local. So there's two things: target _ discard and target _ return. So if you want to discard something, you can just pass this, and if you want to return something, you can pass that. Now I can show you discarding something. Let's say expert if, sure, and then let's just duplicate. Let's duplicate this. Right, we're just gonna use this. All right, so we have a if, and then let's just return 50 here. All right, well let's run it. Oops. Let's run it. Essentially, all it is if c, if this, just a long list of stuff essentially, and all it compiles down to is just ret 50. How that happens is because if you're in a do block contains a list of expressions one by one by one by one. If it's any expression but the last expression, it's going to be discarded. So I loop over the expressions, and since this is not the last expression, or this isn't even a BRK, if it's not a BRK, you're going to have to call expr target with a target underscore discard. More it's easier. So nhir discard expression. It's called in many places, but the one where it's called here is nhir do target. And we're looping over all the expressions, and we're essentially just discarding them. And when you discard them, it forwards this this underscore. It forwards this no target. So in the if statements, when you're setting it, I mean, this 120 is just going to get discarded. 23 is going to get discarded. 59 is going to be discarded. They're pure values. You can just ignore them. Yeah. If you go down here, and it'll match. So go to n default. This is the default expression. It's going to be just some things to match on, and it'll switch the target. Essentially, case target underscore discard. It'll just discard all pure. I'm gonna name this discard pure. Yeah, it'll just discard pure. And how discard pure works is currently this is not completely implemented, but essentially it just matches on things that don't have side effects. And if for some reason it does have a side effect, yeah, this is a to do right here. If it does have a side effect, we just push it. Statements expression, we're just pushing it. Yeah, so target discard, target return creates a new return. Does an R push, returns st diverging. It was called st no return or something, st something. This is called st. I renamed it to st diverging because it represents what I said. If you want to know why this st diverging is a thing and how normalization actually works and how I want it to work, essentially, you can watch the last stream. But it's I didn't really get much done on that stream compared to what I did in between now and then. Yeah, so and then else nhir assigned local with the local as the target. So this is forwarding. All right, so I'm done with forwarding. Let's see. Implement target double. So okay, let's explain. This is one of the simpler ones. I have to open. Not this one. Targets. So essentially, LLVM has this notion of a target triple. Target triple. What is a target triple? Come on, someone's gonna. All right, Rust. So, targets. Okay, no, not Rust. Fine, OS dev. Okay, this is probably one of the best examples. So, LLVM and, well, not LLVM only, but I think pretty sure GCC pioneered this notion of target triplets. So Rust and, not Rust, LLVM and GCC have this notion of target triplets. Essentially, it describes a platform on which code runs. So how it works is machine, so it's just machine, vendor, operating system. So machine, vendor, operating system. You can ignore some sort of things. Yeah, so the vendor field is mostly relevant and usually PC, unknown for like freestanding, and none for other systems. So essentially, I mean, think of it as like the runtime environment, right? The runtime environment. I think like it would say like GNU or something. Yeah, ELF. Yeah, essentially, it's just machine, vendor, operating system. Machine being architecture, vendor being runtime. What, like, it's runtime, right? Your platform, and this thing is operating system. So essentially, what I'm going to do is just arc platform, and how it works is platform. So Linux is a platform. Linux is one of them. So is FreeBSD. Using a arc-platform model, you don't really specify the runtime. This is just linking. Yeah. So WASM, WASI is one of them to target. So WASI is a platform. WASI is essentially WebAssembly system. Yeah, WebAssembly system interface, and it's just like a runtime. It's just a runtime, and this is the instruction set, and this is the runtime. Now, how it works is, yeah, just arc and platform. So arc is architecture, pointer size, endian, ABI, platform. Just the place. I'm pretty sure I have more notions of a place, but like platforms. So what we have right now is AMD 64-C for C code generation. This is a special case. Actually, this isn't really a special case. Anyway, what we have right now is AMD 64-C. So this is the arc architecture, and this is the platform. Platform meaning like standard C, POSIX, all that sort of thing. And AMD 64 meaning 64-bit x86, so we can assume vendor extensions, 8-bit pointers, 8-byte pointers, and so on. Right? And then you'd also do things like ARM C, things like that. So all we have right now is AMD 64-C. So where is that defined, right? How do you get it? Yeah, WASM has WASM32 unknown. Yeah, that's right. So that's for like some freestanding thing. And then you get like WASM32, like mscriptn or something. You get like unknown mscriptn or unknown WASI. So essentially, all it is just target equals target host. What target host does is nothing. It does nothing. So it's just target host, target, arc, AMD64, pointer size 8, platform, kind, platform C. So we do nothing. We do nothing important here. And target string is switch over the target architecture kinds, switch over the platform kinds, perform AS printf, and leak all the memory, and just return a string. So all we do is just call target, assign it to a global variable, and then we, what do? We just printed target string. So let's just take a look where I actually use this, and let's just see how it's defined. So essentially, I have a macro, x arcs, arc MD64, MD64, x platforms, platform C and C. I define all the arcs, I define all the platforms. Currently, all I have in arc underscore T is pointer size. And here, struct target, so arc T, platform T, simple, that's super easy. So I'll show you where I use the target. Where do I use it? Target dot something. I use it here in type.c. So I just created this function called type underscore size of. To do, nothing happens. This is all a big to do, but what I have so far is all the types here, I64, U64, isize and usize are target.arch.ptr size. So I'm just returning that. And yeah, super simple. And there's a reason why I have type underscore size of. This is for the next thing I did. And we can go find out here. Alright, ZST removal plus diverging types to unreachable. Now this ZST stands for zero sized type. And I can show you. Zero sized type. Rust has a notion of zero sized types. So let's just go to Rust right now and see what happens. Go to Rust. Oh, zoomed in too much. So let a equals, no, if num equals 20, erroneous parentheses, this, else, this. Okay, this is a dumb example. This is just a stupid example. We just return, a. Why is this failing? Okay. Yeah, I'm not really a big Rust person. Yeah. Expected I32 found this. Is that really how Rust works? If you return... Huh. Oh, wait, I'm stupid. Yeah, we'll just make this that. Okay, oh god, such a stupid example. Essentially, all I wanted to demonstrate is that if you're working with unit types, it doesn't end up in the final code. So essentially, zero size types in Rust, they get removed in the final executable. There's a rationale that that Rust likes to use to there's a reason why they have zero size types. If you have something like a hash map, right, and it's a generic type of KV, if you wanted to make a type hash set, it's hash map, but with type hash set K to hash map K and that. So this is essentially the rationale of why Rust integrated these zero size types into the language, is because you can do something like this. Let's say you have a hash map with K and V, key value. You have a type hash set with just a key, and that equals hash map key with nothing. And zero size types in Rust, they have zero size. So when you read it, you're only gonna get. It's not even. It's nonsensical to read it. You only ever get one value, right? Even reading it, it stores no size. There's no point to reading it. So what happens is if you have code that uses a zero size type in Rust, it gets deleted. It gets deleted before code gets generated. And that makes these sort of things, these abstractions, pretty nice to have. So, there's a reason why I wanted zero size types gone. For one reason, it's good to have in normalisation. So when I'm normalizing things, I'm making everything statementized and making everything have a nice flow of execution. Control flow doesn't produce expressions that isn't a value. And the removal of zero size types simplifies a lot of things. So if I can remove zero size types before code generation, I wouldn't have to deal with all of these like functional abstractions and like deleting all these things already and things like that, right? If I delete them now, it makes it super easy to translate to C, super easy to just run over and generate IR, generate do code gen. It's makes things super simple. So if I remove them now, I won't have to deal with them in the future. So this is what I did. So let's take a look at this. So this is a function. Function unit equals this. Function unit equals zero size type, and it can be typed like that, but it's just inferred. Unit equals zero size type. So there's a function called takers, takes in an A, which is a zero size type, B, I32. C is a zero size type, returns B. So the type of takers is I32. And we have a function called users. Users equals do block, and then just calling the function takers unit 40 unit. So let's see what happens. Whoops. Clear, run. All right. So you run HIR reorder on it. This is just what gets spit out from the parser, and you have main takers, main unit, 40 main unit. After HIR typing, it performs automatic call insertion, or like UFCS, Unified Function Call Syntax. It just puts these things over here. Because in this language, if you're calling a function, just this unit right here, and it takes no arguments, just simply putting it down will call it. It's like dlang and nim. It's a really nice thing to have. It's not full unified function call syntax. It's just if it takes no arguments and you put it down, it calls it. Okay, so it inserts these calls here and done. That's fully type checked. So after normalization, what does it do? It runs over and essentially it deletes all arguments of zero size types. So if you look at main.takers, it only has B here. A and C are gone. And in main.users, when you call main.takers, it only has the argument to B. And these main.unit calls are hoisted outside before, because they may perform a side effect. Obviously, in this functional type system I eventually want to have, I want to make sure that these functions, you can tell in the type system if they have side effects or not. So if you want to accept a function, like a function pointer, you want to know for sure that that function pointer, when you call it, it has no effects. You can express that in the functional type system. But for now, it doesn't inspect any types, it doesn't do anything. It just assumes. What it does is here in NHIR discard pure, if it matches on default, it just pushes it. Because it's just a to-do. So it just hoists these obviously pure calls out and then just calls main taker. So I mean, this is simple. It removes all this notion of zero size types. So you can't like construct or return them. Well, I am constructing them here, but there's a reason I talk about. There's a reason. Checklist. Yeah, so ZST removal. So deletion of size equals zeros types from function parameters, struct fields, assignments, and all construction in general, really. This is something I'll talk about soon. And the unit type will be used as an imperative lang void type for breaks and returns. So essentially, if you're just doing return semicolon in C, its equivalent in this language is read that. It's just read that. this is not actually being read or being used. It's just a marker, right? You can't have like a null ret, right? So I just use that. We just essentially, the unit type is a marker. Yeah, and the unit type is used for all zeros type, as all zero size types with encompass all types. Yeah, so essentially, let's take a look at this. Type V. Essentially, how you define aliases or newtypes in this language is you just assign it to something, right? But you're not. So this is just type T. It's zero size type. It only has one value. It's similar to Rust's struct v colon. So yeah, so I'm defining a function R, takes no arguments, returns v, and you're just constructing v. And after normalization, it does this, returns v equals do ret that. So like I said, it encompasses all types. It's used as an imperative something. It's like a placeholder. And essentially, after C code generation, it's just void R, void return, done. Simple. So I'm gonna go after this thing. Yeah, let's just create a function. That's what v is this equals 0. So, I mean, for one, you can't even call this function. The innards of the function, like, they're never called. It is impossible to construct a value of the bottom type or no return. It's impossible. As soon as you have an argument to a function which is something diverging, like this no return or bottom here, you'll never be able to call it, because imagine like trying to construct a value of it. It's easy, like constructing a value of a no return is just creating an infinite loop, but it'll just stick in that infinite loop through evaluation of the arguments and never get into the body of the what. So this function, you can never call it. It is literally uncallable. So what you can do is just delete its body. You can delete its body and replace it with whatever you want, and delete the argument as well. So, there you go. What does it do? So main.what takes in an argument of v, no return. Yeah, and then after typing, infer goes to i32 because you're returning that, and HIO normalization. So all it does is just replace it with unreachable UD2. And I'll explain what unreachable is. It'll explain everything. So this is unreachable. So if you've ever seen unreachable in a programming language, it's just this word, unreachable. In Zig, this is an expression. It evaluates to this. Zig's equivalent of this, which is no return. So this, and I think you'd get something like this in Rust, this unreachable macro. Cool. So in my language, it's just this, right? It's an expression that evaluates to no return. And there's different kinds of unreachable. There's different kinds. So if a user was just putting if v unreachable, right? There's a notion of assertions, right? Like you can perform assertions in a programming language, but are they preserved when you're running it in production? So an assert is for debug things, right? If you're debugging, you just leave asserts in there, right? And when you compile it for production, you remove all of them. The compiler removes them all for you, and C it's done with a macro, and Rust is probably done with some other stuff, and Zig it's done with some other stuff. So this could possibly be removed at compile time. I don't really believe in removing assertions at compile time. Probably removing all debug info. But essentially in this language, what this compiles down to is unreachable underscore assertion. So full debug info generates an assertion deleted on production. Unreachable underscore heuristic. No debug info doesn't generate an assertion at all. I'll explain this soon. And unreachable underscore UD2. Minimal debug info, unreachable generates a trap always. So you can see this table right here. Super nice table. It took me 30 seconds to make it. No, it took me 5 minutes. It took me 5 minutes to make it. So essentially, unreachable underscore assertion is on debug mode. This is an assert 0. And assertions, they carry debug info like line info and stuff like that. But on production, it compiles to underscore built-in unreachable. This is a compiler built-in in C. Very easy to understand. It just signals to the compiler that this will never be reached, and it can delete all the code after it, or even inside the basic block. It's dangerous if you don't know what you're doing. And here, unreachable heuristic. It's essentially equivalent to unreachable assertion on production, so it's always debug unreachable. And unreachable UD2. This compiles to built-in underscore trap. Yeah, let's bring back Godbolt. Let's see. Do I have unreachable trap? There's a reason why I named it UD2. So, unreachable trap. What does it compile to? Nothing actually. Wait, oh no, it's built-in trap. Alright, what does it compile to? It just compiles to UD2. I mean, what is UD2? You've used assembly documentation. Generates an invalid opcode exception. Yep. Yeah, all it does is halt the program, it raises a signal, it just kills it, essentially. And this is called a trap, or an exception, or something, right? It's like when you want to kill the program, but you don't want to tell anyone, like, you don't want to, like, have any debug info or any of this things like that. Essentially, it's just a single instruction. And what I mean by this is unreachable UD2. So it's minimal debug info, and it's unreachable. It generates a trap always. So essentially, this will never be deleted on debug or production, and it compiles down to the simplest kill the program instruction, UD2. So what I mean here is, what it does is, since V takes an argument of no return, it can never be called, right? And it just goes down to unreachable UD2. So why does it go to unreachable UD2 or not other things, or not even leave an unreachable? Now, we can't really delete symbols. Let's say you exported this. I don't know, you did like exports. I'm still not sure on what syntax I want to use. Probably like, I wouldn't mind a double square bracket. I think it looks ugly, but I wouldn't mind it. So let's say you exported this main.wat. You exported it. Imagine like you call it in some way. Assembly gets a hold of it, or C gets a hold of it. I doubt it though. I don't think I'll. Anyway, let's say something gets a hold of it, because at the end of the day, it's a symbol. It's an exportable symbol. If someone calls it, and you don't leave this unreachable UD2, it'll just keep going down and release like whatever uninitialized memory or initialized memory is there. It'll just throw a bunch of errors and stuff. If it's explicitly a UD2, it'll tell the user that, like, whatever you just called, don't call it. Yeah, what I'm trying to say is it's better than nothing. UD2 has to be there because it's the simplest thing. It's unlikely that you'll call it. So if it's unlikely, you don't need to leave debug info. So I like this idea of a UD2. So essentially it's, I mean, even here. Yeah, I don't know. I don't know what code you have to put in here for Clang to generate a UD2. I think I've seen it before. I've seen Clang generate a UD2. GCC doesn't like to generate it. Clang generates it for like certain undefined behavior, but I think GCC just moves on. But I've seen UD2 be generated by Clang. Essentially, this performs the same thing. This is the same action, unreachable UD2. So, yeah, essentially what I'm trying to say is we just use the functional type system to guide us. Like, if this has a parameter that cannot be constructed, the function can't be called. So, yeah, that's just one of the things. So, I'll use another example. So let's just take this thing I prepared before. So, function loop is a loop, infinite loop. So what this compiles down to, what this infers, type inferred, is to a no return. So we'll just delete that. So this function is a do block, let a equals loopin, and it returns a. Essentially, you can't assign a value of no return to something, but it'll still type in the eyes of the functional type checker. It sees that this is fine. But essentially, what it compiles down to is just that. It never gets assigned anything. So what happens? Let's run it. So main loopin is just loop main that HIR typing converts that to a bang. Yep. Typing converts it to a call and BRK. And after normalization, main loop turns into, so the loop keyword, the loop expressions, there's no loop expressions. But now it's just a do block and you just repeat over and over and over again, and just that. And here, in this function, it calls main.loopin, and it just puts it unreachable, heuristic. So this is to let the further optimization passes. So in my language, I think I'm going to have an IR, like my own IR. So this would be nice to tell my own IR that we know we know for a fact that any code after this is unreachable. So we could probably do something, we could probably like, what you could do is, you could do something like this, right? Let's just do like let's do like main dot, let's just make some basic assembly. Here. And then you can do like, 1, 2, 3, 4, and then just do this, JMP that. So this is a tail call. It's a complete tail call. And if this wasn't unreachable, you'd probably have to do like call and then ret, right? But letting the compiler know, this is nice. So it'll know that it can never go back here. Nothing will ever happen. So you can just perform a tail call just like that. That's one of the nice things about this functional type system and having a notion of things that can't return. Because if you know they can't return, when you call them, you can just insert this right after. Yeah, so I think that's it, right? I think that's it. Yeah, call handle returns with the unreachable heuristic. So I explained that. ZST removal. Yep, diverging types are unreachable. Yeah, I think I explained everything. Oh, okay, side effect correctness. This is the last thing I need to explain. Side effect correctness. So let's try this. Side effect correctness. Here we are. This is one of the best examples. So this is a function called from underscore lvalue, takes an I of slice, I32, returns nothing. So let k is a u size equals 0. Let g. This is a current limitation sort of thing. Remove that for now. I don't think I'll explain during this stream. It's nothing important. But here, essentially, we're assigning g. So g equals k plus plus. You're indexing into I. That equals 0. I mean, what's the order of evaluation of this thing? It's basically this. K plus plus, get the value of k before the plus, assign that to g, index with g to I, equals 0. It's really hard to follow. Well, not hard to follow, but from a compiler perspective, what do you generate, right? Whoa, that's not right. Type size off. Oh, no. Okay, for now, let's return something above 0. Okay, I'll come back and fix this. This is just an example. All right, so HER underscore typing. So let k equals this, ig equals k, 0, brk with empty tuple. All right, so HER normalization. So main.from lvalue takes an I of slice I32, k equals 0. So let's just put these side by side. Oh, come on. All right, side by side. Yeah, okay, sure. Hopefully my camera's not blocking it. So g. So essentially we're recursing all the way into here. So we're just doing k plus plus. So k equals 0, just from here, but everything is. So we're creating a temporary value, k plus 1. K equals 3. K equals this temporary here. Yeah, so Yeah, and then we use the previous value. So we use the k. I think we use the k plus 1. I think no. We're supposed to store the original value of k. All right, let me just fucking make a reminder for that. Stupid. All right. Okay, essentially just hear me out. Yeah, so this temporary value gets assigned to G, and then you're indexing with G, so we're taking a pointer to this L value, and then we're deref assigning it. Okay, so that's a lot of indirection for something that should be pretty simple. But in reality, it's not. This is one of the examples that I created. Let's just copy this. Alright, we'll copy it, and then we'll do something like this. And I'll modify the compiler to show. Okay. Alright, so we're running it, and essentially we're creating these pointers, and we're using this like more than once. So in the eyes of how expressions work in this language, let's essentially turn this into what it's supposed to look like. So let's take this expression here. How it works is we're doing this, we're essentially performing this, right, and then using the value. Oh, let's say you did yeah, you're essentially doing this, right? This equals that. It's kind of like a duplication, and then you're returning. Yeah, okay. Here's how assignment expressions work. Let's say you have a equals something, and then the value of a gets returned. So this is C assignment expression semantics. You can do something like this. K equals a equals 20, which essentially compiles down to k equals a, and a equals 20. So assignments in this language are expressions. So what happens if you did this like really naively? You did let's say a equals that, right? If you did it naively, what it would compile down to is I plus k, and then a equals plus k. So you duplicated this HIR expression node. Essentially, in the compiler, like a compiler like yesterday, right? What it did was it just duplicated the expression, right? I mean, you can't do this. What you have to do, what's right is creating a temporary. So you can do this. Let's go 0 equals address of that. Equals 0 and a equals that. Just so you don't evaluate it twice. And this is this thing of preserving effects, right? I'm preserving side effects. You only evaluate them once and once only. So this is essentially what is outputted. You're taking the address and you're doing that. So essentially all this code does this. And how it works is in normalisation. So normalisation does all the heavy lifting. It's called... Yeah, and when you're performing expr assign, it calls expr.deassign LHS equals LNHIR L value. So you're essentially taking an expression and converting it into a non-side affecting L value. Checks if this is an expr local, return expr else. Obviously this to do everything. Yeah, so essentially it creates a new pointer type, creates a new local with that pointer type, creates a new ref, expr address of, assigns the local, so underscore 0 equals the address of expression, and then essentially returns a deref. That's what it does. That's how we make that's how you make L values in this language only have no side effects. They have no side effects at all. So if you like duplicated this a bunch, you can assume the compiler, like from what the user sees and what the compiler sees, it will only evaluate it once. So we do that by creating intermediary values by taking the address of things. All right. I think that's enough. What do we have right now? 45. So, okay, this is what I want to do this stream. Okay, hold on. Explain a bit. Hold on. All right, so let's go to what I want to do. Scroll all the way down. I don't think it's here. I think it's somewhere else. Is it here? It's not syntax, right? It's such an old document. So enumeration spreads, sparse arrays, struct init. Unwinding. Where did I put it in compilation strategy? Ah, here it is. So, it's under exotic typing. Okay, this is just some random words. Essentially, I want this language to actually do something useful. So, how to do something useful? You need sumtypes, you need generics, you need all of this higher order type thing. So, this being a functional language, you'd find it surprising that no, I'm not going with ADTs. Well, I do have ADTs in the language, things like that. But I'm not having this named like Rust sort of thing. You have like an enum, all right, enum t. You have a field, and that's also a struct containing these normal things. I don't like it because it introduces these extra namespacing. You have extra namespacing here in the field. Essentially, I just want to refer to the field. So what you have in V is like you define all your types, and then you have a singular type t equals field equals dot 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 dot. So we have this thing called a sum type. It's essentially summing of types. It combines them all together in essentially a tagged union, and we'll perform optimizations like Rust does, like a null pointer optimization, like using the sentinel values and things like that. But this is just what happens. It's instead of using these enumerations, it's just these pipe things to do sum types, and this is how it is in C. It's how it is in the hair language. Other languages probably, but this is the most elegant solution to me, and you'll see why I eventually went up with this design. Because it's not these types being composed into a namespace of a t. It's just t holding a sum of multiple types, and you don't have to match on this namespace thing. You can just match on the type. I'll explain as I go on. All right, this is me talking about the bang operator. Okay, so oh yeah, I'll explain this after. So equivalent of vlang strconv common parse uint2. It's just a random v function that I took. I wanted to duplicate it and show how it is in this language. So this is a function parse underscore uint2. It returns a s slice of u8, turns the base 32. It's mutable. Bit size is u8, and what it returns is u64 or a parse error. And parse error is just an enum, not enums that you'd see in Rust. This is enums as in integer. So you can perform something like that to make the backing type of a parse error u8. How you do it in Zig is you do that. How do you do it in V is you do that, right? Pretty simple. So when you call parse uint2, so I'm calling it with s, base, and bit size, just these random variables, and I'm matching. So you can have these inline type annotations inside a match pattern. So you can have this v inline u64 to v. So essentially I'm unwrapping it, and air just maps to unreachable. So like I said here, possibly omit the parse error annotation. So you can have this parse error. The checker would automatically figure this out for you. It would just delete that and put unreachable there. And you can use you. You would be a type of U64. So, yeah, it's this notion of like this or that. And in the Hair programming language, they use this a lot. And they wrote an article on it. It would be nice to read it. Hair language, hair lang. Safety features. What was the error handling? I think it's this one. I want to read this later. All right. I think it's this one. Here, tagged unions and error handling. Okay, so tagged error handling in Hair is essentially really equivalent to mine. So you're essentially matching on a variable binding, and you're matching on its type here. And inside works like that. So Hair has this kind of sumtypes. In this language, I want it as well. V has it as well. So how you do it in V is essentially you'd create a type, like parse result equals. Actually, no. In V, you'd use custom error types. I'll just go over pad matching. So you just go match parse uint2 with whatever you're calling, and then you'd this in here. Then you'd go U64, and then yeah. So what it is you're matching on types. So you're just matching on types. So what? So it makes it easier. It essentially makes it easy. You don't really have to think in this sort of like namespace sort of thing. It's just types to types. I really like it that way. I prefer a simpler language, right? I want namespacing too. I want namespacing to be module only. Russ really wanted to just get all the C++ isms. I don't like it, right? That's why I didn't go with ADTs. So, let's implement them. Let's implement them right now. So we have nothing in here. Okay. Let's just revert change. Delete that. Revert. No. Great. So let's create a function. Okay, let's define a struct because we implemented that before. Let's go struct foo. X is an i32. And we'll go here. We'll create a function that constructs it and returns it. So we have to create type parsing. So let's do that. Foo make foo. Foo 20x. So I think I talked about its syntax, right? I think I talked about its syntax. Surely I did. Analysis. Oh my god, I'm gonna have to be searching for this. I apologize profusely. Oh, whatever. I remember it. Okay, so there's only two kinds of struct expressions, struct literal expressions. You have the foo with the colons. These are designated initializer syntax. It's like in C. In C it'd be x equals that. In Zig it'd be exactly like that. But in Rust and in V and in my language, I want it exactly like this. And what you'd let's create another field. This in V, y would be initialized to a default value. In Rust, you always have to specify every single value. In my language, I want it to be like Rust, but also you can put this here. I'm not sure if Rust has this. V has it. Anyway, so there's only two kinds of things. So you have this designated initializer syntax where you can omit some fields. And in here, you can have this thing. Actually, no, this isn't right. No. Yeah, so it's either designated initializer syntax, or you can omit the types, omit the fields and make them go one by one. So I want to support 2 of these things. And you can parse these things unambiguously. So where's the error? So I inserted an assertion failure somewhere. Yeah, parse expert, pexpr fallible, right here. Okay, so here is where the implementation is. Tuck, open, curly braces, OCBR. So compile to two different kinds of expressions, later on perform fully qualified kind. Okay, so it's just a T, 1, 2, T, A, B, and then struct update syntax, like what JavaScript has, V has, Rust has, XS. That's the fully qualified syntax, both of these. No, sorry. Okay. So, to do impl assert not read. So let's implement it. We'll take the... So right now we're in the parser, so I don't think you guys have seen much of the parser. So, we are going to... First, we have to check, is it this one or is it this one? The easiest way to check is if it's either this one or this one. You can simply check. So, right now, we're at this token. This token is the semicolon. We go to the next one with pnext, which is this right thing here. And then we can check the next token. If we're right here and the peak is a colon, we know that it's this. Else it's that. One of the good benefits of having this sort of like curly brace sort of thing. It's good to have. So let's check if p.token dot p.peak dot equals stock colon designated initializers, else positional initializers, and then we'll just assert not reach that. Hello Kirby. So then we'll do this, and then we are right. How are you? I'm good. I'm good. So peak.kind equals stock colon, and we can just go over them over and over them. So how it is we'll just copy one of these things. While. Yeah, we'll take this one. This one's the easiest one. Actually, no. We'll take the one for this one. Alright. Essentially, how it works is p.token kind, tuck, OC, closing brace, so OCBR? CCBR. Keviro says, when will I get mod? Nah, no one needs mod. My server, my text doesn't need moderation. If it needs moderation, I'll moderate it. Okay, so in the body, essentially you're just checking if it's closed brace. If token.kind equals comma, go next. And if p.token kind is not equals that, you go to comma or all that. Alright. So designated initializers, you just do this. I stir T field lock T field lock pnext so pnext, and then you're at X. Alright. Okay, and then you're right here, and then we just do a HIR expert T P expert. That's one of the smallest. Okay, we're just performing parse the expression. So we need to do 2 things. So we have the list of expressions. So let's just create a. No. We need to find a way to model this in the AST. So how are we gonna do it? It'd be nice if I could find where I wrote this fucking thing. Constant perfect hashes, blah, 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 blah. Struct. How do I make it search only in one place? Crits Creek. Hello. This looks like an ML. No, no. It's more like a bastardized version of Haskell and Rust with like sprinkles of V in it. I'll show you more of the language when I get off of this sort of thing. I'm just trying to find out where I wrote this because I have more stuff. Struct, right? Struct init. Oh, come on. Okay. All right, figured it. All right, so how are we going to represent structs? So there's two ways. You either have the position initializers or designated initializers. So let's go here. I think we're going to have expr struct desig. These were designated. Designated, and we have okay, just expr struct and expr struct positional. And then expr struct is supposed to be the canonical type that the type checker not desugars, but essentially converts this to this. Canonical representation. So let's go here. Struct. Destruct. Yep, destruct. It's going to be a list of fields with the field name, location, type. I think that's it. It's just field type. Imagine if we had tuples in C. How nice would that be? Okay, struct. Actually, I've never what am I going to name it? HIR struct field T. Okay, so it's just name possible type. I don't know if we need to store type, but we didn't need name and lock. Alright, HIR struct field T. So it's just a list of these fields. Usually when a type checker creates an alternative representation, you say the type checker performs an elaboration as opposed to desugaring, which is purely syntax based. Oh. Really? I've never heard of someone say elaboration. I've always assumed it was desugaring. Like type to desugaring, just desugaring sort of thing, or canonical representation. I just say canonical representation. Yeah. So anyway, destruct is a struct field T of structs of fields. Okay, so it's just name to lock and Negvorsa. Hi, welcome to the stream. All right, so HIR struct field. I think I'm just rename it SF. That's easier. Struct HIR SF positional. No. Position doesn't need to store anything. Okay, so we essentially struct. This is like designated initializers. It's just SFT. And here it's just D struct positional is just a list of HIR expressions. Easy. And we'll go up to the top. We'll just type def these. Good. So we construct a HIR init. We'll construct a HIR SFT SF struct fields equals null. Could be pointer. Just use STB arrays. Push. I'm going to create a HIR struct fields SF. Great. Field. Why is it not named field? It's field. Good. And expert is expert. So we're going to heap allocate. And just push it. Great. And position initializers is even easier. Actually, I missed this. I needed to put Phoenix and then. Great. All right. Well, let's do the same. I think this is right. List of expressions. Talk cspydr. No. Push. Yeah. pedo-token.com next. cspydr. For what language is this compiler is built? So you mean what the compiler is compiling? My own language. It's just my own language. This is this is my 17th stream. I post on YouTube, all the VODs on YouTube. It's one of my programming languages. It's gonna replace C for me, and anything I write ever. This is essentially where essentially, it's like I want to own the tool chain. So I own all the software that I write. Not in the sense of owning it, in the sense that all bugs belong to me or something. It's where it's I don't like I love writing in C. I love writing in C, but uh I need these things, like I need closures, I need sumtypes, all these things like that. Like C is nice to write. C is nice. I love writing it, and there's reasons why C's lived this long. But in my program language, I want it to be my C replacement. So it's gonna be really functional and all these sort of things. It's got generics, module system. I mean, there's other languages I've tried. I've tried like V and things like that. V, Go, Rust. They're not for me. Zig's not for me, surprisingly. Things like that. Cool. No macros. That's the thing. I'll have to think on that, right? Because this not like C macros, right? It would be more like Lisp macros, but I don't know, right? I don't know. I'll have to write more on the language. The thing is, you don't really know if you need it until you need it, right? I'm not just gonna go add features just because I want to. I need to make sure that I need to have them. So when this language is basically done, I can start writing in the language, find out what I need, and implement it. So macros is something that it's not, I don't think it's controversial. It's just like, do you even need it sometimes, right? And there's cases in C where you do need it. I use it all the time with like X macros. You can see this, like I use X macros all the time, right? It's just X macros, X macros, X macros, just everything. Uh, I use it all the time, and I'm trying to think of ways. Like, I mean, how could I do this sort of thing in a language that doesn't have macros? So with V, it would have like comp time. Zig would have comp time as well. Rust has their own Lisp macros sort of things. Definitely controversial. Macros mean your language isn't expressive enough. Yeah, that argument's never made sense to me, really. No. Macros are supposed to reduce typing. They're not for expressiveness. All right, so let's just create an expression and return it. LLVM, no way. Never using LLVM. Okay, expert struct. What I'm planning to do is I'm gonna generate the mode of compilation which is most important right now is C code generation. I'm gonna generate C. At the start, yes, I'm gonna generate C. There's a reason why I want to generate C. There's multiple reasons. One is portability. If you imagine someone on their computer taking a compiler, like cloning it, right? Imagine if the bootstrap was a simple cc space c file enter. This is where things like, I mean, there's two constant things in a Linux machine, right? There's a shell script, there's your sh, and your C compiler. Usually these days, sometimes the C compiler is absent, but it's just so easy to install. If I want someone to get my compiler up and running quickly, as fast as possible, right? And without a binary, or even just running code or like things really quickly, I'm going to generate C, and that's one of the reasons. One is portability. Two, it's essentially for performant code, generating C is much easier than generating LLVM. Now, not for the reasons that LLVM is bad, in the sense of it's generating code. LLVM is bad is because it's a moving target and gives you problems all the time. It's a big fucking mess. It is huge. It is so fucking big. It is probably, I don't know, it's grown into this disgusting mess that I don't want to touch ever. Um, not because I can't do it. I don't know. I have nothing to prove. The thing is, Zig. There's a reason why Zig's moving away from LLVM. I talked about this in one of my other streams. Zig is moving away from LLVM and embracing their own code generation. Like I said before, rolling your own code generation gets fast enough code faster, right? So fast enough code faster. Essentially, um, my compilation speed with Clang is like twice as slow compared to GCC. Why? It's because of LLVM. Compilation with Rust is unbelievably fucking slow. Compilation with Rust is so slow. One, because the Rust compiler is just so huge. Probably all of its like performance stuff is just like loading in new code pages into the cache. That's probably where all the slowness is. And the other slowness is just LLVM just being huge as well, right? Because what I'm trying to say is GCC is more performant than LLVM in generating code. Essentially, fast enough code faster, right? Zig's V compiles so fast. Zig compiles fast when using its native backend. At the end of the day, for fast user development and fast compiler development, you want like sub 100 millisecond compile times. When I was working on V and I was working on the WebAssembly backend, I could compile the whole compiler in 200 milliseconds. 200 milliseconds. It's like a live reload at that speed, right? It's like a live reload. So imagine I'm working on the compiler, the whole compiler code base. I press enter. 200 milliseconds. It's done, and then I can just run the compiler again. It's having a fast compiler is one of the most important things. You try that in Rust, good luck. You know how C++ users, they complain about editing a header file and having to recompile everything? Edit a crate in Rust. Edit a crate in Rust, and then just having to recompile that, and then like imagine if it's like statically linked and all these sorts of things. And I don't even think I'm pretty sure Rust is caching, but not caching on the LLVM side, because there's like I think you have to compile everything as a unit. I don't know much about Rust, but people complain, right, when they're working with like game engines like Bevy. It's like I think they're trying to fix it in some sort of ways, but like doing crate splitting. I know it's a big issue with the compile time of Rust. Solution number one: get rid of LLVM. Get rid of LLVM. It's really just become this thing. And imagine what I want to do is if I want to harness the power of LLVM, I'll just compile C. And I have access to every production compiler in the whole wide world. I have access to the C ABI, which is the lingua franca. Fuck. You know, oh god, one of my first ever talks, I was talking about the V programming languages at some uni. I think like I was practicing like lingua franca. It's franca, right? But I think I said I was trying really hard not to say franqua on stage. Yeah, I was practicing that for like a good 30 minutes. Yeah, yeah, it makes sense. Good decision. Yeah, so it's like LLVM, like it's just one of the worst. I'm not saying that LLVM is bad. It's just in reality, it's not one of the best choices that people say it is nowadays. I mean, V had a LLVM backend, and they just stopped maintaining it because LLVM was such a moving target. It just just costs too much to maintain. Not cost too much, but it doesn't stay stable to LLVM. There's breaking changes all the time, like Zig, Rust. They complain about it. They have to pin LLVM versions. It's I don't know. I'm all for reinventing the wheel. So I mean, even simple code generation isn't even that hard, right? Just like create control flow graph, stick in your files, read a paper, implement like these sort of things, and you have a pretty simple code generator. Or you could even just do what V does and have native backend and run over the AST and generate machine code. That's the quickest thing. That's what TCC does, Tiny C Compiler. You know, you can get incredibly far without LLVM, and don't let anyone tell you that you can't, because you definitely can. Don't let anyone tell you that you can't. All right, so we have expr underscore struct. This is essentially struct with designated initializers. Yeah, it's just setting, just runs over all the stuff. Okay, so for this one, do this one. Expr equals no, not tuple. Expr struct positional, and we have a d positional equals exprs. It's for the follow, Neg Wilson. And we'll put a continue here. All right, great. So my my Pratt parser or Prieston's climber, it would have solved the braces thing. We need to store. Okay, no, we need to store the backing expression as well. I think it's just called expr. Yeah, expr and exprs. And expr equals expr. Oh, I hate trying like that. Good. All right, now it'll just. This is the parser done. I'm pretty sure. And we'll get a assertion failure when it goes to print it, and I can go fill that up. Unexpected that. Expected top level statement. Oh, wow. Okay. Why is that? Oh. Okay. Let's put the to do. Okay. Assertion failure. That is a purple one. Visit successes. This is on my reordering code. Go destruct. Yeah. Expert. Direct is true. 4. Yeah. What's the problem? Oh, struct fill. Dot expert. All right, good. And then break. It's just right. Okay, good. Good. Yeah, I think that's right. Another one. Oh, expected value got type foo. Ah. Okay, that's simple. Visit successes HIR import. Okay. Because the struct in it's supposed to be a type. Cast. Yeah, visit sanity type. Right. Let me think. So this is being parsed as an expression, and now essentially it's just a tree. But what I have is in this here HIR reorder passes, it goes over and performs a topological sort over all the symbols in my program. It does something wrong. It's supposed to check for a value, right? Expect a value got type, right? I have to convert this on the fly from an expression to a type. So we can do that though. I think I'll just create a function called Odin has many built-in type like int big endian. Does this make sense? Uh, no, I know. I know types like that, like the big endian type. It's pretty cool that they have those built in. It's really nice that they have those built in. Yeah, endian with a e. Okay, so we have to convert here. So he probably doesn't know what it means. No, yeah, endian e. Yeah. Wait, oh, does this make sense? What are you referring to, Neg Pulsar? Symbol expert to type. Hmm. Byte swap representation. Yeah, like specific endians. All right. What do I switch? Comment. Export. You'll eventually see this is needed. Default. What module is it? Global variables, such a stupid solution, but I am really not ready to insert a million parameters. Module. Okay. Good. Let's go to tutor. Okay. All right. All right. So we have so it's just mod name. We do it before table. Table resolve. All right. Name and mod. Okay. Right, and then raise an error, because it has to be error. Expected type got value. All right, and then we call, what is cost call? Visit sanity type. So we need PO. That's all we need is PO. Return type. Yeah, kind was type symbol. Symbol. All right, good. So, the reason I'll explain what I just did, because it took a while. Let's say you have make foo equals foo. So essentially, we're parsing this as an expression, which means anything can end up on the left-hand side, which is not right. Possibly. What about string UTF-8 C null? You mean like data types in this language? Like constructing them? This is only for structs. What I'm doing right here. Okay, so right, okay. Yeah, this is what I was going to explain. So let's say yeah, this main.foo. Okay, so this is pretty unambiguously parsed. Obviously, on the left-hand side, it can be whatever you want. So we have to make sure that it's right. So we perform this check not inside the checker. We perform this inside HIR underscore reorder. So this is the reorder pass that sorts everything topologically. We also perform things. We perform things like infinite type size analysis. Make sure there's no cycles. Mutually recursive functions without type annotations. We check that here as well. Just the little things that help build a language's correctness. Having these things are really nice. And it puts things in a nice topological post-order sort for people to go over, like the further passes. Yeah, so essentially, this is an expression when you turn this into a type. Obviously, you know for sure that that type is that type, but you don't know it yet. For all you know, it could this could happen. You could do let foo equals something. You could do that. So this would resolve to a local, and what I wanted to do is not resolve to local. I wanted to resolve all the way up here. So what we do is we call this fucking symbol x for the type. All it does is take an expr underscore local, takes its name, and just constructs a new symbol. It just tries to resolve, and then we just call sanity function. If it's expr underscore symbol, we just do that again. And good. So this is still going to run. Expected value got type foo. So let's just, before it errors out, let's go check. Expr. Let's see what type it returns. And we'll print it. Let's print it. Wow, why is that failing? Huh. Why is that failing? Why could it be -1? So where is this being called from? It's being called from visit sanity time. Oh fuck, expr.type. Okay, so we so stupid. Type. What's that? And then you call on the type. Get expressions type. Alright. Good. So struct main.foo. Easy. Easy. Now what happens if this is before it though? Nope, still main.foo. Which is good. We passed the post ordering. Okay, so now we've actually resolved the type to foo, so we can go down here and essentially I think replace it. What are we gonna do? So okay, we'll rename this to void visit struct expr in post order, and what we need to do is construct a symbol. So I'm gonna go over here. Symbol equals expr t.sim equals break. What we need to do is construct a new symbol. So expr dot equals lock equals expr dot lock dsym equals resolve. Adding more keywords like var would help. Help in knowing where a struct initializes. Pretty sure Zig has this notion of this dot notion. I think Zig has this dot notion. It'd be nice to have this, but I don't like introducing extra syntax where with a little bit of compiler stuff you'd be able to find out. See, this language isn't ambiguous at all. It's just trying to extract the type from the left hand side where you need to check for things like that. Alright, so we're just gonna convert the local into a symbol. Yeah, type, right? Yeah, type. Type T type. Type equals type new. Make a new one. Type equals this. Symbol equals symbol. Symbol. Alright, and then we just set type. Personally, I found Kotlin syntax impressive. Yeah, I really like the Kotlin syntax. Especially with like lambdas, and they have like inline lambdas as well. Uh, it's a nice syntax. It's really nice. Very simple. It's always good. All right. So we have duplicated code, which super annoying. So I'm just gonna move this down here. All right, good. All right, you got symbol type, easy type, return nothing. We'll still visit it. Okay, visit struct expr, and then we're just gonna call this. Done. PO destruct dot expr, right? This expr. Make it return type. Type T. Return type. Alright, we go expr.type equals this. Expr dot destruct dot expr. And we'll pull that here as well. Destruct positional. Okay. And good. This is a good sign. This a session failure, because this is in the printing stuff. And when we can print, we've basically done everything else. So where's fields? Expert field. All right, then we can print this in. Case. All right. So no, I'm going to do print. Okay, great. No, great. Good. Okay, let's do case. Positional. List of expressions. Why is this erroring? Struct SF. It's D. the field. Okay, that seems fine. What is it generating? Okay. Unreachable. What's it trying to print? Okay, typing. So now we're in the type checker. This is the simplest ones. We're not gonna do much type checking. We're not gonna do much. Let's go export field. Let's go down below and implement it. So case expr struct. We use struct positional, but what we want right now is just x to 20. To do defaults. Okay, so just go over one by one. How are we gonna do it? So ready set inside the order pass. So what we need to do is extract what is it? Extract the type. Yeah, we need to extract the symbol. So we'll get the underlying struct type because yep. Okay. The type. Thanks, copilot. So struct. So we essentially have our rsimty. We have a reference to a type symbol. So we have a struct. Yeah, essentially, what the type symbol is this is a type symbol with type symbol kinds. Currently, it's only one kind. This is a type symbol struct. So essentially, it has just a list of struct fields. T symbol sf underscore t. So we get the fields. All right, what's in the field? Type lock field lock. So let's go over them one by one and try to match them. Let's go over one by one. What we need to do though is we'll need to do a O of, is it an O of n squared? O of n squared, but n is small. Thanks, copilot. This is what I usually write all the time. Go over. Okay, so we'll go over. It makes it easier to understand if we just go like this. So equals. We'll take the length of this, and I is less than c, I plus plus, and we will O of n squared it by doing this, and we'll have to make sure duplicate initializers aren't set as well. We're just looping all over the place at this point. Fuck, it's like O of n squared plus n, but like that's a constant factor. I don't know much about big O notation. So, O of n squared, but n is small. I think I should check for duplicates in the parser. You know what? Okay. Assume no duplicate fields. Parser. Parsers check that. And we'll add a big to-do. Yeah, we'll add a to-do here. To-do. Duplicate field init. Check for this. Okay. So let's just assume no duplicate fields. So we'll go over them. We'll go over the fields one by one. We'll need to search for we'll just create a generic function that takes in a field name and returns a type symbol struct field. So we'll just do this. Do a type type symbol t type. We'll just do it like this. So we need a t symbol sft field equals null. Okay, and we're just gonna go find it. We're gonna do o(n) squared and just go find it. Right. So if equals null, where's an error? Field not found in struct. Great. And then we'll have to do it would bm r value. Perfect. So this is the field.type, and then we'll have to get the field expression. Expert field. We'll take this. If field equals field, and then pass in the expression here. Expression. Not expert.lock. It'll be field lock. I'll get the I-T short name. Actually, no. Actually, I found in struct, and we'll just get the type. No. Alright, then we just have the type. So we need to perform a C unit, we'll perform a unification. C type unify. Field type to type. It's perfect. And that should be it. Right? Right? I think that should be it. Oh wow, where's that? Where did that come from? Yeah, it's an oyster. What's the parser doing? Why is this happening? Session found not line. Sprint. Negative 109 ... I don't know where the fuck that could come from. And I have F sanitize on. No undefined behavior is being done, but that fails. What the fuck? Oh, another Heisenberg. Please not. It better not be. Use of uninitialized. Okay. Use of an uninitialized value. But it doesn't tell me where. It doesn't tell me where. This is what GCC tells me where, but Clang doesn't. So you better pick this up. What the fuck? See, use of uninitialized value. So, okay, how do you get... UB-SAN not showing line numbers. You need to use ADDR to line. Oh my god. Okay, I don't know how to use this. How does it work? How does it work? Option addresses. Okay, default is a.out. Okay, good, because I use a.out. Alright, let's just copy this address. Can't believe it. So, I hate ADDR to line this one. Alright, so this is this stack trace, cproc. Alright. I'm not, and it's the read of uninitialized value is expr field itself. I wonder where is the uninitialized value coming from? Because I just checked the parser, and I assign this is literally a designated initializer. Everything has to be assigned, otherwise it's 0. So I don't know. Is this like memory corruption? I assume not. Come on, thanks UB-SAN. Here, so this is the address, right? ADDR to line paste here. Fields I. Oh fuck. U32I, I'm duplicating them and clobbering them. Are you fucking kidding me? Oh my god. Oh my fucking god. Oh my fucking god. Yeah, don't trust the code that Copilot writes, because that went me on a tangent. Don't trust the code that Copilot writes. Because I would have called that if I wrote it myself. Yeah, I feel dumb. But I feel dumb because I just dumb. Okay, so I, J, great. Alright, good. Type size up. This is where I want to be. So let's just return a size of 1. To do. Please fix. Alright, HIO normalisation. So that's it. So oh, J++, you said. Ah. Thank you. Fuck. Thank you. Saved my life. Okay. Yeah. HA reorder. Okay, this is what the parser spits out. HAR typing. Assigns type annotation to main.foo. Struct init of the main.foo. This is embraces. This is a symbol. X20. I think I want to remove the braces on printing. I could do that. Table. Okay, print symbol. Just do that. Good, now it's constructing it. So main.foo constructing of x. All right, normalisation. Do I do anything here? No, no, no. I just do the normal stuff. So let's just do a case express struct. We do. So we just do a. We do. Okay, now we just need to loop over all of the fields, perform a diverging on the expression. Break. Okay. And after normalization, good. We get a main.foo with the equal sign, and then now we get a do block with a red. Good. So this is one of the things I wanted to get done this stream. There's another thing that I want to get done. I want to get sumtypes. I want to get sumtypes. So, I mean, how are they defined? Essentially, we'll have to get type aliases as well. So let's just do type aliases right now. Type t equals I32. We'll just have we'll just name it alias. And this is going to raise an error, isn't it? Unexpected type, expected top level statement. Do we have a talk type? We do. We do have a talk type. So let's just match on it on top level statements. Let's just copy this, paste it, and find where that error comes. So case talk type. We need a p type. P type. P alias. That isn't taken. So this is a big function called p struct. So let's construct the alias. So let's parse type aliases, or essentially newtypes. Semantically, these are newtype. Okay, I don't need all of these, but I think it got it down. I think that's it. Okay, I'm gonna read through this just to be sure. Next, check talk ident name lock. Next, pnext talk assign. So we'll do tutor. A ZST. P expected talk assign. Lock T, type lock, token not lock. Equals P type. Okay. I think that's it. So what we need to do is we need to extend the type symbol kind with a alias. So we'll do it here. Struct. Okay, type T alias. Easy. Does it need type lock? No, it just needs type. No, it doesn't need type lock. It does. It does. All right. That's it. That's it. I think that's it. So enter. Unexpected EOF, expected top level statement. I don't know where that comes from. GDB. No. B long jump. Just want to catch it. Ah. Break. My fault. All right, visit successes type info. So, type types of alias. Does it work? Type on error, visit successes type, PO RSIM type, on error. Visit sanity type on error. Wow, that's simple. Yeah, it's Copilot gets pretty good when it gets accustomed to your code base and your specific code styles. I write in a very specific way. Well, it's not very specific, but it is consistent. I write in a very consistent way, especially with the ways I call my functions in specific order, the ways I name my functions. Variable names is very important. I use the exact same variable name if that variable name has the same purpose shared over multiple places. So it's very easy for the AI to just pick up on these things. Type symbol alias. Wow, it's simple. Type dbb str alias dot type. All right, alias, alias, alias. After all the passes, nothing happens to it. So let's use it. Ret alias. I don't want to cast it, but I just want to do 20. So without the cast, it just does an I32. But with it, let's see if they can unify together. Expected main.alias got 20. So I want to... do I make it an explicit cast or an implicit cast? An explicit cast for now. Okay, 20 main.alias. Good. So let's put these in sumtypes. EXPL. Sum is a bool. Let's do uth2 or ith2. Let's do that. Unexpected that, expected top level statement. So in type parsing, I have this kind of Pratt parse sort of thing. Yeah, explicit cast. Yeah, explicit cast. It you see, it would be okay if it's not newtype, but I have like a newtype idiom, which means it's like constructing a completely different type. It's not really an alias, so an explicit cast would be better, really. But I'm kind of thinking about an implicit cast as well, but I'll think about that later. So unexpected pipe, expected top level statement. So let's just get to parsing this, which is pretty simple. It's just here, parser util, right? Okay, so this is the type parser. The function is called ptypexpert with a precedence. This is Pratt parsing or precedence climbing. It's the one that I use in my normal expression parsing. And I use it for types as well. This makes expression or type parsing really easy when there's precedence involved. So unary call. I think, okay, so case pipe. Yep. Prec call. To do. I've got this in precedence. All right. Case. Tuck pipe. Now we have a next part of the sum type of the sum type. Okay, to do. Same to do as above. To do as above. Okay, so we're gonna perform p next. Strong type versus alias. Odin has both key cases, I think. Keyword alias. Here, Odin. No, Odin. Hmm. Come on, alias. Advanced types. Type alias. You can alias a name type with another name. Okay, that's nice. Distinct types. No, allows for the creation of a new type. The same underlying semantics. So, this is what I mean by new type. Like, new type, no space in between. So, this is like a Haskell thing. Yeah, so I think I want to be able to swap these out. I want it like, here, you know what? I'll put a dot down because Odin, seems pretty nice, and I put that on my checklist. Alias. Yep. Okay, so it was above. Cool. Function. Oh, we need to create a type for the sum type as well, by the way. So let's just do that. We'll do type sum. Type sum. That's good enough. Okay, and then we'll create a struct. D sum. It's just an aggregate of all the LMs. Great. Type sum. What's the point? What's the args? Okay. Yeah, this code is incredibly messy and ugly and also not performant. These need to be implemented properly. But I can do that later. Okay. LMs equals NPTR. Yep. Doing this mem copies allocations type. All right, so we do type sum and dfn the sum dot lms. It was lms. Good. Good. All right. Visit successors type. So we need to visit the type. Actually, there's no need. Not here. The specific semantics. All right, but we'll get another session failure. Yep, visit sanity type. Okay, so let's do this. Case type sum. I don't think it needs any sanity. It just needs to run over all the elements. Yep, that's good though. And we get another recession failure. Yeah, I love littering my code base with the sessions. It makes things a lot easier to just go and check and update. It just tells me exactly where I need to go. Yeah, alright. Just write up type case type sum. So, yep, no. We'll do menu. Oops. And we'll do this pipe. Right. It's not right. Why does it only have one U32? Pretty sure this is in parsing though. Hold on. Why is it not raised in the session failure? Here. Okay. Type. Wait, it's supposed to be red. Okay. Args is type and then construct a new type. Okay, so I need to change the semantics of this. Just lm this. You're doing a mem copy of all the old ones and pushing in the new one. Okay, so lms. Yep, pushing in the new one. Well, now it's just I32. How does that happen? Ah. Just type, and then you're pushing in the LMs. Yes, okay. So type main.sum equals U32 plus I32. Now, was that in the wrong order? Nope, it's in the right order. Wow, good. Then the type parsing. I think that's it, right? We'll put a pointer here. See what it does. Yep, pointer, great. cspydr. cspydr only has aliases to the point where all struct and enums are anonymous and only receive their names through aliases. Yeah, that's that way would be better for me. Now I'll explain why. Uh, I have these two different worlds, right? One world is all the symbols, and one world is all the types. All the types are interned, and all the symbols are interned, right? If you want to access if you want to bind a type to a symbol, you have to construct a symbol that references a type, and then construct new types that reference the symbol. Well, not new, yeah, to construct types that reference the symbol. So there's a notion of type symbols, like a representation of types, in like representation of types like in a symbol. So we have structs and aliases, and then all of the anonymous stuff in types. So we have sumtypes, function types, concrete types like integers and something like that. So we essentially have these two worlds. It would be a lot easier if we can just have one thing which binds a type to a symbol and call that an alias, and then have everything else as anonymous, like you have, and I think Jai and Odin does that as well. These anonymous structs. It would be nice to have, really. Yeah, you're right. You're right. It's who knows? I think I'm gonna put a note down. I'm gonna put a note down. Unify See, I don't remember why I don't remember why I went with two different worlds. I'm pretty sure there's a reason because I changed it. I originally had it that way. But I changed it. I'm just trying to remember why. I'll probably think of it after the stream, but I'm pretty sure there's a big reason why. But I don't know. But for now, this is all that I wanted to get done. I streamed for 2 hours. I streamed long enough time, but I think that's all I wanted to get done, really. So what did we do during the stream? We did sumtypes, aliases, struct init. Okay, that's good enough for me. So what am I gonna name it? So what's this current stream number? Oh wait, I don't even have my the stream still says FPLC lowering to LAR. I just keep forgetting to change this stream in first. All right, so norm 16. So this is the 17th stream. So we implemented so we touched the parser tracker table. Yeah, so we touch these things, and we'll do hash 17 because it's the 17th, and it'll be type. So type aliases, sumtypes. Type aliases, sumtypes. What's the last thing that we did? Struct init. Okay. Enter. Sync changes. Alright, so I'm gonna end the stream soon. So if you have any more questions, you can pop them down. I'm just gonna write a couple notes. Is compile time code execution something you're planning? Yes, 100%. Yeah, it's gonna be like Rust's compile time code execution, so it'll compile down to another representation, which you also perform more analysis on. But it's also just is it kind of I don't know if it's efficient to interpret. I don't really care about efficiency at compile time. Really, when it comes to compile time evaluation, a tree interpreter is fast enough. Zig does it. I talked about this before. But yeah, it doesn't matter what format you use to interpret. I'm just planning to do it in an IR, like what Rust does. Just implemented last week for cspydr. Had to rewrite half the compiler. Wow, really? Man, that must have taken ages. All right. Yeah, struct parsing can be implemented unambiguously by greedily searching, unified type symbol, aliases. So, I did a lot today. But I think that's where I finish. All right. All right. Goodbye. Thanks everyone for showing up. Cspydr. Dynamic reordering of the different types when checking passes was the main point. So you mean accessing everything in order. So before I go, I'll just explain what I do in my compiler. I think I talked about it last stream or the stream before that. Yeah, so you're reordering. I wonder what algorithm do you use? Because as an algorithm that I use, I'll just explain what the reorder pass does. And if you want to read my source code, it just says here. This reorder pass orders symbols topologically so they can iterate. So a further passes can iterate over symbols dependency free. So it's you need to get the symbols in the right order so you can go top to bottom easily. I feel like yeah, that's one of the really important things. So to get compile time code execution, you need to you need to check this before the next one. Yeah, so the reorder pass order symbols topologically, so that further passes schematics. Next one, you have two ways of resolving a symbol: deep and shallow. Yeah, I think I have a notion of that direct and indirect in here. Yeah, so all this does is 5 different sanity checks. Does this symbol exist? Is this type cyclic without indirection, so infinite size? Is this global cyclic / self-dependent without a indirection? Is function self-recursive without return type annotation? Is this symbol used in the right context? Show logics, ADTtypes, deep type of function, global type. Yeah. So I have a singular algorithm, which is the sort of graph coloring depth first search. It is the simplest things in the world. The Python implementation on this website is literally like less than 20 lines. It's like even 10 lines. And it does all of these things at once. All of these things at once. Symbol exists. Type cyclic, global cyclic, like infinite size, self-recursive, symbol used in the right context. I use this for everything. And it creates a nice ordering. Yeah, so that's what I would have gone with. Cspydr q.c. Yeah, I want to read this. It's been a while since I've checked out your compiler. Report recursive dependency. Okay, great. This is kind of what I do as well. Yeah, good. Stack size. This is like kind of I don't know what kind of graph traversal this is. I wish I knew. But it's some kind of graph traversal. Cursor stack buff. Yeah, good job. Really, really good job. Yeah. These are like one of the most important things to have in a compiler. Just like even like dependency checking. Yeah. All right. So. I'm done. I'm done. So goodbye, guys. So just thanks for showing up and everything. Yeah, I really enjoy streaming. The thing is, I have like school and stuff, so I can only really stream on the weekends. And today is the weekend. Today is Saturday. Where I am. But goodbye. Good night, everyone. I'm gonna be going to bed as well. It's 2 in the fucking morning. So good night. Bye, everyone.